Hello, everyone. Mr. Hine is back, and today we're talking about 151, which is just a summary of position velocity graphs and understanding the connection between those. So here's where you should be at, where you should be. All right. Because this video, there's not anything new. This lesson, it's really just a recap of what we've done. So if we look at a position graph, and hopefully now you know that position graph is a better word for than distance graph, for the pure reason that we talk about displacement rather than distance, right? But we'll call this position graph d of t, and this is t, all right? And it can look however it wants. We'll just draw something that looks like that. Keep going, for example. And here's what you need to know on position graphs is that the velocity is the slope on a position graph. And because that's its slope, or you can think about it as its rate of change. I always just use ROC, right? That's its rate of change at a particular, time t. So on a position graph, right, this is your zero, and every slope on it is how is its velocity changing, its rate changing, right? And the other part you want to be at is that average velocity is the slope. So it's still slope between time a, how should I say this? Average velocity is the slope between two times t equals a and t equals b for that time between them. So if you want to look at the average velocity between time 2 and 5, what's the slope between points 2 and 5? So for example, it would be at A, you're at the point A, comma D of A. At B, you're at the point B, comma D of B. Remember that I'm calling this function D of T in this graph. So then the average velocity would be D of B minus D of A over B minus A. Because this right here, for lack of, I guess now I'm getting to it, is the change in displacement over the change in time. And that's really what average velocity is right there. And maybe I got carried away by trying to give you an example and generalizing it. But really it's just the slope between 2 points. And we'll just put that. Average velocity is the slope between 2 times, i.e. it's the slope between 2 points. All right. I don't want to overcomplicate things necessarily. Okay. And I do use displacement because, again, these are usually displacement graphs, so be careful with distance. And then don't forget, I guess the last thing I'll add here is that distance is the absolute value of displacement. All right. Displacement can be negative. You can end up behind where you started, but distance, you wouldn't actually account for that because distance is always positive. It's always accumulating upwards. All right. So that's everywhere you want to be on a position graph, is that velocity is the slope, average velocity is the slope between 2 points, and don't forget distance is the absolute value of displacement. As for velocity graphs, right, it can look however it wants for some time t. We'll call this v of t. And I'll make a graph that looks something like that. Why not? I actually don't like that. Hope you're not copying along. Let's do one that looks like this. Okay. And where do you want to be at? Well, displacement is the area under the curve. And I keep using that word displacement, but in case you've got what displacement is it's like a final position, how far away, or you can think about it as, i.e., how far away from its initial position. That's what displacement is. Is its final position, and how far away it is from its initial position, kind of. So displacement's the area near the curve. The slope of a velocity graph is acceleration, right? Because that's how velocity is. That's how velocity is changing. And if you wanted to find average velocity here, don't forget that it's the change in displacement over the change in time, in which case displacement's the area under the curve. So to get average velocity, if it's a velocity graph, you have to do area under the curve to find that value. And I think that's it. And then just as before, I'm going to mention this, distance is equal to the absolute value of displacement. And I say that because that's just one of the most common mistakes here. So if you wanted this, if we went back to this distance, this position graph up at the top, this is a displacement graph. If it were a distance graph, the graph would look something like this for reference, where it still goes up, but at that time when it starts going down, it's going to reflect over the x-axis to remain positive. Right. And that's a distance graph because your position would be going backwards, you'd be going behind where you started, but if it's distance, you keep moving forward. That's still a positive value that you add on. So when you find area under, so if this were, say, velocity, and you're finding area under the curve, that's why we talk about displacement as a negative area, because that's going to affect your final position rather than if you just keep accumulating upwards. So that's where you want to be with position velocity graphs, is all of that. And then the last part I want to talk about, and we'll look at an example here, is, and again, feel free to pause the video, pause it at certain times. Hopefully I'm saying everything right. I believe I am. And if you think there's something wrong I'm saying, please call me out on it, ask me about it, and I'll clarify for the class. All right, so let's look at an example, because you want to be able to, the other thing you want to be able to do is, given a velocity graph, and technically is also true for position graph, but we'll start here, is be able to, and we'll do 4 things here, and that is answer like, when is the velocity greatest? We'll answer, when is the speed the greatest? We'll talk about, when is acceleration positive versus negative? And then make sure you can also determine when your speed, when are you speeding up versus slowing down? And that's kind of where you want to be at here too. Okay. So if we make an example, the graph, time t, this is a velocity graph, v of t, and say it looks something like this. Okay. So it's a different example than you've ever seen in the book, but a velocity graph can look however it wants. So remember that everything up here are positive velocity values, which would mean that you're moving away. 0, when velocity is 0, so when v of t equals 0, that means that you're standing still. And then everything down here below the x-axis is negative v values. So this is when v of t is positive. This is when v of t is negative. And that would mean that you're moving backwards. Right? Now do note, if you're watching this, I'll put a little star. A velocity graph does not tell you where you started from. You could find how far you traveled. Like if you found an area under the curve, you would find your displacement, which is how far from your initial position you are, how far from the initial position. But a velocity graph does not tell you where you started from. It does not tell you its initial position. And that's a limitation of velocity graphs. Okay. So let's answer these questions here, and then I think there's enough for you to do the lesson, and also as a recap of the last few days. So when is velocity greatest? We're looking positive, and we'll put that right there, and we'll call that point A, because it's the highest positive value. When is speed greatest? Well, notice that this value is up 1, 2, 3, 4. That's about 4.5. And down here, now remember speed, I guess where I'm going with this, is the absolute value of velocity. So speed is only positive. And down here, you have 1, 2, 3, 4. That's around -5. So that actually means right here, which I'll call point B, your speed is the greatest because the absolute value is a higher number, right? If you want to make a speed graph, all of these two curves below the x-axis would flip, in which case point B would be higher. Point B would be somewhere up there if you would have flipped this over the x-axis to make it a speed graph. And acceleration, again, is the slope. So when is acceleration positive? Well, that is from here to here. All of these are positive slopes. And then acceleration is negative all along here. And then acceleration becomes positive. And then your acceleration becomes negative all the way down. And then it flips and your acceleration becomes positive again. So if I was to call these points, say D, E, that's it. So positive would be from 0 to point D with a union of E to A. And it would be negative from point D to point E and from A to B. And I guess I missed something over here because from E to A it's positive. It's also positive from B to, we'll call it G. I think I'm making this more complicated than it needs to be. I hope you're hanging in there. And then speeding up versus slowing down. This one gets confusing. So remember that for my point here is that 0 is you're standing still. And for me, I have to visualize that to remember if I'm approaching a still position, right? If you're approaching a still position, you're slowing down. You can't come to a stop without slowing down. Okay. So anytime you're approaching 0, whether it's from the positive velocity side or the negative velocity side, you're slowing down. So that would be, so you are speeding up. So you're speeding up is when you're moving away from the standing value. So you're speeding up right here from when your velocity is positive and your acceleration is positive, because you just stood still and now you're moving away. So you're speeding up on this interval here. Use colors. Colors will end nicely for this. So speed up I'll do in highlighter. So you're speeding up here. You're speeding up here. You're speeding up here. And you're speeding up here. So all those parts I highlighted, you're speeding up. In which case, that's when you're moving away from rest. So that's when velocity is positive and acceleration is positive, as seen in the first highlight or the third. Or it's when velocity is negative and acceleration is negative. If they're both negative, if your slope is negative and you're negative velocity, notice you're in this right here where you're moving away from standing still. You're moving backwards from a rest position, which you have to speed up because you're no longer standing still. And on the flip side, slowing down to end this all, slowing down, I'll put in red, is from here to here, here to here, that interval, and that interval. And all those you are slowing down. And what you'll see on those is you might have when velocity is positive and acceleration is negative, right? And that's the star right there that I'm referencing. If you're approaching still position, you're slowing down. Notice when your velocity is positive, you're up above the x-axis, and acceleration is negative slope, you're approaching still position, which is slowing down. Or you could have in this position when velocity is negative and acceleration is positive, in which case you're moving away, but you're moving away towards rest, so you're slowing down right there. So that's an overview of everywhere you need to be with velocity and position graphs. I thought it'd be a quicker video than that. Hope that makes sense to you. Please come to office hours. Send me an email if there's any particular problem you want me to look at or go over with you. And good luck with all of this. End this video now.